Okay, at this point, we are ready to talk about the Prenex normal form for first order logic. If you remember last week, we discussed conjunctive and disjunctive normal forms for propositional logic. And normal forms are usually a canonical way to express logical statements, or they have certain properties that make certain procedures easier. And the Prenex normal form is a normal form which will help us employ inference rules when we encounter first order logic statements, and we will come to that later. First of all, what does Prenex normal form look like? The Prenex normal form for a first order logic statement involves quantified statements at the beginning, and finally it has a part where you do not see any quantifier. So essentially what you would like to do is we would like to collect all the quantifiers at the left hand side at the beginning of the statement, and you do not want any quantifiers at the right hand side. So for instance, this example in the previous slide, this one here, you see I have a quantifier appearing here. Therefore, this is not in Prenex normal form. What I would like to do is um, apply some transformations on the statement so that its meaning stays intact. Okay, it states exactly the same thing, but I would like this expression to appear at the left-hand side of this expression. Okay, so in Prenex normal form, this part where I have the quantifier is called the prefix, and M here, which has no quantifiers whatsoever, it's called the matrix. Okay, so this is the procedure listed here. This is the procedure to put a first order logic statement given to us, uh, how to put that into the Prenex normal form. We start with anything that is not an AND or an OR. If you have NAND, NOR, XOR, of course, implications, biconditions, etc. First of all, get rid of all those, replace them with ANDs, ORs, and negations. Okay, and usually you will not see XORs, NANDs, etc. when dealing with these, but you will encounter a lot of conditionals. So those are the main things. So what you need to do is, of course, P implies Q is equal to not P or Q simply, or a biconditional, that's two-way. Okay, so the first thing, get rid of those. So just have ands, ors, negations in your statement. Then, if you have negations appearing in front of quantifiers, then get rid of those, diffuse them inside towards the matrix. Okay, so I just want to have quantifiers here. Okay, no operators, no negations, etc. So if you have any negations appearing in front of quantifiers, just move them inside. That's the second step. And clearly, of course, to do that, you have to remember the Morgan's laws in first order logic. For all x px is equal to there exists an x, not p of x, and there exists p of x. I should have negation here, that is forgotten, and here. Not there exists an x, p of x is equivalent to for all x, not p of x. Okay, so that is the second step if you have, of course, negations. Number three, to move the quantifiers towards left, we would like grouping, and we would like distributions, and collect the like terms together within a single quantifier if possible. So for this, recall, we have seen that for all, the universal quantifier, it distributes over AND, but it doesn't distribute over OR. And on the other hand, the existential quantifier exists, it distributes over OR, but it does not distribute over AND. Okay, you have to be careful about this. And in this step, Renaming variables is a tool you can make use. And in general, we call this standardization, and we'll talk about this later again when we talk about inference in first order logic. In general, when stating your propositions, let's say, uh, make sure you use different variables for every statement, which will then avoid, which then you can avoid confusing statements. Okay, so remember, you can collect, for instance, if you have such a statement, for all x p of x and for all x q of x. Here you have for all quantifier along with and. Therefore, you can collect these two, p of x and q of x, together within a single quantifier. So that is for all x, p of x and q of x. You can write this. Of course, if you want, you can write this also as for all x p of x and for all y q of y using standardization. Okay, but if you have this, that will make it easier. Similarly, if you have an existential quantifier along with an OR operation, there exists an x p of x or there exists an x q of x. Now you can combine them together. There exists an x p of x or q of x. However, if you have the other way around, with for all, if you have an or in between, for all x p of x or for all x q of x. Now, remember, these two are different statements, essentially. So they have different meanings. They have different domains, maybe. So these x values, they are not the same. The x here in this portion and the x in this portion are not the same because you have separate quantifiers. You have two quantifiers here, okay? So x here is just a variable. It's a placeholder. You can replace it with anything you like. That we call standardization. Now here, since I have universal quantifier along with or, I have to do standardization. Okay, I have no choice. I have to change the name of one of these variables, and I will have to write for all x p of x or for all y q of y. Okay, and now since I have different variables here, I can write this as for all x, for all y, p of x or q of y. Okay, now you have to understand the difference between this one and for all x, p of x or q of x. In this one, for this statement to be true, p and q functions have to be satisfied for the same value of x. Okay, p of x or q of x, this statement have to be satisfied for one single value of x. In fact, all of them. But in this one, for this one to be satisfied, here, these x and y values can take different values. Okay, so that is the key. Similarly, there exists an x p of x and there exists an x q of x. Here, since you have existential quantifier along with AND operator, you have to do standardization and change one of the variables. And therefore, you have there exists an x p of x and there exists y q of y, and write there exists an x, there exists a y, p of x and q of y. Here again, x and y can take different separate values. Finally, the last step, you combine quantifiers at the left-hand side, and as we have just seen, you can collect statements within quantifiers if the variables do not match. For instance, you have for all x p of x or for all y q of y, you just put the two quantifiers at the left, since this for all x doesn't affect q of y, and since this for all y doesn't affect p of x, I can write them in this way. So that's in general given here. Q here stands for a quantifier. It could be for all, it could be there exists. Quantifier x, f of x, and g. And g here is either a propositional statement where no propositional variable appears, or no predicate appears, therefore x cannot affect it. Or it could be a predicate function where um, it depends on some other variable, for instance, like y or z, etc. Okay, so if you have something like this, you can write this inside the same quantifier. So that is quantifier x acting on f of x and g of x. Sorry, f of x and g. G doesn't depend on x here. Similarly, if you have an or in between, it's essentially the same thing. Quantifier x, f of x, or g, that's equivalent to quantifier x, f of x, or g.